Hello, back for yet another day. I'm going to be working more on the virtual machine. I want to get it into a working state well enough to start dumping all those same assembly instructions into like we were doing in day 5, I think. Oh man, I need to mute my stream. It's actually working. Okay, so what do we got to do? I added a few to-dos. I stopped streaming, and then I was like, well, damn, lots of stuff is broken. Guess we don't need to do that. Load into register locally. Yeah, I don't need to do that. I need to start cleaning up these to-dos. Okay. This is the first one. So, well, first off, when we shift this number up, like let's say you have 255, you shift it up by 8 bits, and then you AND it with 255, that just erases that higher value. And also, you want to do this instead for the, let's see, oh, I think I'm confusing myself already. Whatever, we won't worry about this for now. So we're just not going to AND that. Depending on whether or not we want a little or big endian. We'll do that eventually, we don't need it right now. Let's go to what we're mainly going to be working on today. We're going to be talking about operands. So these are operators. These are the actual instructions that we feed to the virtual machine. But to decide what kind of operator we want and to append operands to it, we need let's do operand type. And so these are modifiers, or rather specifiers, for the kind of operator that we want to do. Like if we have an operation where we want to move from a register to a register, well, this is where we'll decide if those are actual register values or immediates or addresses or offset addresses. So we could do operand, reg. Well, let's do operand none first. Register. We have registers, we have immediates, we have addresses, and we have offset addresses. But really, we can combine that offset into that address. We can just assume that assume all addresses where you do this. Like you wrap it in brackets, and then whatever that value is in the register, you go to that location in memory. And for all addresses, unless it has an offset, we'll just add 0 to it all the time. So we can just keep it nice and tight. So we have registers, immediates, probably bake labels into that, and then addressing. I think that should be good enough for now. And that should help us clean up the way that we, how do I put this? The way that we sort through those tokens. Let's go down to where we, oh man, I already scrolled past it. Didn't get that much sleep last night. Emit bytecode, yeah, right here. Why can't I jump to this? Isn't that interesting? Hello? Okay, I can't like control click it, oh well. Just gotta stop using the mouse. So, we could define these operands like that. And then we could, you see how we determine the kinds of tokens that we want to use. We're going to read ahead. We're going to send a token into a thing called, operand type. Determine operand. Yeah, why not? And it'll take a token. And then we'll just return operand none for now. So the idea is that we don't know what the op type is yet, and then we're going to want to read in all the different tokens, feed in the token. And one problem that I left in the engine last time, I'll just run it for you. So we read the MOV, register, and then number, but tokens have the ability to store the value directly inside them, so I don't even need to have a number following a register or a number following an octothorpe. I can just store that value directly in the token. And that's what we're going to do in VM parser. If I can find it. So right here, where we determine if it's a register, we can defer this add token until we can determine the actual value. And we can remove this, that part where we change it to a token, change it to a number. So we're just going to see, okay, so we read the R value, like if it's R0, that means that we want to access register 0 in that command. And so we know that it's a register. We're going to read ahead. We're going to determine what the value is. And then we're just going to put that directly into that register token. And the same thing for that dollar symbol. Register. Oh, but then this will also be tricky. I'll also need to do that whole read ahead dance thing, and yeah, we can do that. Just bloat it up a bit more, why don't we? It's not that bad. Just extract the number here too. Oh yeah, and so I also experimented a bit, and I understand why this is happening now. I do the Control-Alt thing, where you create a multi-cursor on different lines, then I do Control-C, and then I want to paste it somewhere, right? When you Control-C, when you copy every line, that also copies the new line. And so instead I want to do like Shift, hold Shift and do this, and then paste it, and then you see it doesn't add a bunch of new lines. So just something annoying that I had to deal with. So I think this should put us into a decent space to store the integer in the token. I feel like I'm missing something. I hope I'm not missing something. Let me check how the number parsing itself works. Yes, I think when we read the dollar symbol, I want to... Oh no, we already do that right here. We read the dollar symbol, and then we advance I before we read the next input. Yeah. Okay, let's see how this works. And of course, we hit an assertion because now our tokenization has changed. And so we have mov reg1. Let me also go to print tokens, and we'll see that, you see how when I print it out, I also print the integer with it. And so we can do that for registers and octothorpes as well. Just make it a little bit prettier. Like that. And then we should start being able to see the value stored along with that register, or the immediate value. I think we might be reading it wrong. So we want to store an immediate value of 1 into register 0, and so we see register 0, but octothorpe. Okay, we're still reading in a number token. I didn't fix that right in the parser. Yeah, let's see what happens when we get here. Let's just step into it. Huh. Oh, oops. Oopsie, that's my bad. So this is for registers. We also need to do this exact same thing for octothorpes. Yeah. And again, it's messy. We can, once we have all the different cases worked out, we can always tighten it up later. Okay. Register 0. Huh. Doing something wrong. We're reading in mov twice. That's because I never add the token. Man, it is a bad day today. I am not working too well. Let's see what happens now. Okay, mov register with an integer of 0, octothorpe with a register of 1, with the number of 1. We're going to have another mob command with register 1, moving 2 into it. We're going to add register 1 to register 0. Then we're going to add register 0 to register 1, blah, blah. Now what happens? Oh, yeah, okay. So then, now that we have condensed the amount of tokens we're reading in, because we no longer have specific number tokens, now we need to adjust how we determine what operator and operand we're using. Just, this is the general process. You make something messy and then you clean it up. And we're in that process of cleaning up that mess. And now we're going to go back to determine operand using that specific token. So we're going to read in, oh god, we're going to read in that, we have the mob token. And then after that, we're going to determine the operands for it. At the beginning of every loop like this, we're going to assume, for now, that the first token read in is going to be the operator. And then from then on, until we hit another operator token, the rest of them will just be operands that will feed into this function. And we can start with that right now, if we can just remember it. So we start out, we're just going to set the op type to none, the operator type. This can be flexible later, but for now we'll just assume that they're in 4-byte increments. We can start incrementing it variably later depending on the type of instruction, but I can't imagine having those instructions for a little bit longer. So we're going to get the starting byte code, which will be, in this case, it will be evenly divisible by 4. And then we're going to advance it by 4. We're still going to store the starting byte code. And we don't need to worry about these anymore. We can just take these and... Well, this will be the decision tree. So we're not going to do this just yet. This will be the decision tree that then gives us the final operator that we want. Because, that's what we're doing right here. We're assigning that op type to a certain kind of operator depending on the tokens that we read in, but instead we're going to start working with this operand type, and you'll see if my brain recovers just enough to start being able to do this. So right here, as long as we haven't hit the end of file, we're going to get the operator token, and then we're going to read in the next token. And depending on what that is, we can just do a bunch of if statements. You just say, parsing, assembling can be slow, because ultimately, the runtime will be slower, and the cost will be amortized. If it becomes a problem, we can speed it up later. We can always... Later. Not really. Little smiley face. Just to put an excuse in there for the total slop we're going to slop it up with next. It's going to get really sloppy, folks. We're going to do operand type. Operand 1 equals determine operand. I think that's it. And then we'll feed in tokens I, the next token. And we'll just see what happens. We'll see what needs to happen, at least. So this compiles. Yeah, let's just run it once and see what kind of token we end up with here. So this will be... What is I here? I is 1. Oh god, yeah, okay, so we're not... When we're dealing with the global tokens array, we can see every entry, like VM tokens, so we need to open it up in here. So the token that we're dealing with right now is a register, and it's going to have a value associated with it, so... Yes, we will, we'll do that. We'll determine operand. Where's determine operand? Okay. So we can just do a switch statement for now, or... Yeah, just another switch statement right now. T.type. And we can do a default case. Case, token, register. Then we can have an octothorpe, Or we could have, to get it ready, we could have a left bracket. And then we can just return operand address. We'll need to add more information to it. Return immediate. Or we can also handle just raw number tokens in here. We'll just also treat number tokens. We can actually do this. If it's an octothorpe or if it's a number token. And we'll let it fall through. So if it's a number token, it'll just fall through the octothorpe case and it'll just process as an immediate. We can always fix that later if that assumption proves to be incorrect. So we should also store, we should just make struct enum operand. And this will be another tagged union, and we'll have operand type, and then we'll have a union. And I think I want to start storing all the unions, like, you know, we just have data. We just put data in there. And just make sure this compiles first. Operand type. Is that not the same thing? Struct missing tag name. That's so weird. My control click isn't working anymore. That sucks. 2388. Struct enum. Oops, I meant to do typedef struct. Okay. Where was I? This is tough. I am exhausted, people. Okay. So we can just change every instance of data to as, and we'll just see what happens. That actually works. That's crazy. Will this bite us in the ass later? Like, what if I want to do, e as? Okay. So now, this is going to be a change right here that affects everything beforehand. Is this a bad idea? I don't really know. I just didn't like how we store the data in union and just call it data when we should cast it as something. I don't know. It's flexible. You know, we can always change every instance of as. Well, there's a lot more instances of as than there were data. Should I make it a bit more specific than data instead of just vague like data? I'm on the fence. I really don't know what to do. Well, no one's watching. No one really has an opinion. Well, for now, this can be an ongoing question, but for now, I'll just leave it as data. Because when we changed it just now, it didn't have any trouble. But for now, we'll just continue the assumption that data stored in the union can just be accessed as data. So we'll have the operand, which can be an integer for, well, I guess we should have a union of the different types it could be. Because it could be a register, or an immediate value, or reg immediate plus offset. I guess it doesn't really matter. Yeah, it doesn't matter. We're not going to have too many of these anyway. We don't really care. We can just store it all. We don't even need a union. We can just say regnum, or just reg imnum, because it can only either be a register or an immediate value, and then we can do offset, which we store like value. Not really sure. It doesn't really matter. Register, immediate, reg or im, I don't know, whatever. It doesn't matter, we're just wasting time. Okay, so now we're going to have an operand. We're going to return an operand from this, and we can just do operand op. We can do op.type equals that. And then at the end of it, we will return the operand. Op. Oops, I mean op. Of course, we're getting more errors because we never changed how we call this from below. And so if it's a register, we'll do opreg or immediate equals t.data.integer, the same as the immediate value. If it's an address, we'll need to read this differently, because if it's a token, if it's a bracket token, then we'll need to read the next token. Oh yeah, this could be tricky. So if we read that it's an opening bracket token, could mean that a register is in there, or it's an immediate value in there, or it's any combination of register plus offset, or an immediate mode plus an offset. So there's potentially, I mean, there's always going to be a closing bracket, or there will be an error. So there's always going to be at least three tokens. At most, for the time being, 4 tokens. We're not going to allow you to chain together pluses. It's going to be very restrictive. So I guess we could make this a while loop, or we could pass in the token count, or next token. Pass in the next token, and then it'll be a pointer of tokens. Yes. Okay. And we'll need to adjust this a little bit. So this will potentially grow larger. Then we'll need to do if well, let me figure out how we're going to call this in the first place. Determine operand. So we're going to want to pass in a reference to I, pointer to I, and then we're going to want to pass in tokens. Determine operand, operand op1. Yeah. Left data must have struct union type. 2400. Tokens.type. Okay. So now we're passing in the, oh my god, please. We're passing in the array of tokens from the base offset, indexing it with I, which will be the current. And so yeah, we can just do we can just do token T1 equals tokens at next token. Then we just switch based on T1. T1. We'll just make these T1 for now. Okay, so that allows us to compile. So once we read in that token, we should do next token, like dereference it and increment it, because that means we read it correctly. And then we'll want to read in the next one. We just do, yeah, we'll just do token for now. Just change it all to T. Change it all back to T. Or flip-flop. Then we're going to read in the next token. If it's an opening bracket, then that means that the next token will either be, it could be a register, you can switch again, t.type. It could be the same cases, case token, reg. Please, I can't type today. Default. It could be a register, it could be an octothorpe. It could be a number. If it's anything else than these, like even if it's a right bracket, then there's nothing inside, so it's an error. You do, I don't know if we need that case yet. But if it's a register, otherwise we'll have an error. I think I'd rather do, if it's a register, okay, we'll need to have a more specific kind of operand in this case. So if it's an address, we'll need to know if it's an address using a register or if it's an address using an immediate value. So we can do addressed reg or addressed immediate. That gives us a bit more flexibility. And then we'll still assume that it's going to have a numerical offset along with it. So we can do off type equals operand address reg or operand address immediate, and we can move this down to the octothorpe because they're the same thing. Make it fall through. If it's a bracket, we'll do processing error and return 0. I don't know, we'll just return op. Or, yeah, okay. We'll just handle that in default. I want to have a right bracket there. What are the errors? Operand address 2405. Oh. Maybe register. Oops. Yeah, that is not my day. So we see what the next token is. Depending on what that is, then we'll do the register or something or something. And then after that switch statement, we'll need to append opt.reg or im equals t.data.integer. Same thing right here. And then we can see if I'll try to read another token. Let's do this again. Well, I guess it doesn't matter, just to save some space, because we're going to need to do this anyway. We can do if no, let's do this. Going to need to increment the token, then we'll read in the next token, and then we'll do if t.type equals, it needs to equal a token plus, otherwise we'll stop here. If it's a plus symbol, have an offset, else we're just going to set the offset to 0. Well, you can just do that right here. Yeah, you don't even need that else statement. So we'll increment that same thing again. We'll do a next token plus plus to get the next token after that plus symbol. And then we'll need to check if t.type equals token num or t.type equals token octothorpe can handle both of them. And then we'll do this again. Go to the next token. Read the one after that, and then we'll do up.offset equals t.data.integer. It's kind of verbose. But this should handle every case for now where it could be a register or a number or an octothorpe or a bracket to mean that we're addressing memory. We can handle labels later on. I'm hoping or imagining that we could backpatch labels to mean a register or an offset or something like that, so it doesn't really matter. I'm trying to think. Yeah, labels are just going to be an immediate value, meaning an address to a place in memory. So it'll work like a constant number. You just won't be able to change them. What I mean is that you can have labels in the code, like label, and then underneath it, like if you define it in the code, then underneath it you could have a bunch of instructions like this. Or maybe you could do like .u32 x, set it to 100, and then that would be telling. We would have routine to parse this and go, okay, x is going to be stored at the next available slot of memory as a global value, as a u32 with the value of 100 right now. And then whenever we see x showing up later, we'll just replace that with whatever the x gets evaluated as a constant offset in memory. Yeah, memory, yeah, whatever. I can't type today. Meaning, oh my god, dude. X is the first global defined, so in the memory it'll just go to slot 0. So whenever you see add x, it'll be like, it'll result in this. And you can't add like a register to a constant value, but you could do something like x like this, which gets replaced when we're assembling everything to an actual value. So that's what I'm talking about when I say labels, but we're getting ahead of ourselves. Don't worry about that right now. I'm all over the place. I don't think I can stream that long. I'm really tired. I don't know why. Well, yeah, I mean, I know I couldn't sleep that well. Okay. So we read in the tokens. If it's a plus symbol, otherwise we're going to want to read in the next token. If it's not a plus token, we're going to, it needs to be t.type equals right bracket or token rbrac. Otherwise, like, we'll also need to handle that in here. We can cut back on duplication later, but I'm not feeling that smart right now. Okay, so then we need to go. Okay. If it's a plus token, and the symbol after that is, oh man, my mental bandwidth is it's gone now. It's a plus token. We're going to go to the next token. Once we read that, we need to go to the next token. And it needs to be a closing bracket. I can't type today at all. Otherwise, it's an error. Can't type. So we're going to jam this in everywhere that I can think of. It's going to be a right bracket. Okay, okay. So here's what's happening. We read a left bracket, we check what the type of the next token is. It has to contain a register or an immediate value, something. Otherwise, if it's neither of those, even if it's a right bracket, we're going to call it an error. I can do printf. We're going to need to add a lot of debug statements to this. This is our basic debug tooling that we need to start doing. We can do, well, error token will read in token error. It reads t.line, and it prints error line. So we would need to print the VM line. So we could just do token VM token error. Why not? Who cares? VM token error, print line, print VM line. Okay. Let's go back down to 2445. Go with G 2445. Okay. Please. 2445. Okay, I need to press enter there. VM token error. We'll do T. And then we'll do expected. There's a big bee, a big fly? Is that a bumblebee? What the hell? Did you guys see that? I hope it's not in my head. That is crazy. Okay. I have a big bee in my room. Expected VM token error. Expected. Dude, I can't focus at all. This is crazy. I'm so tired. Okay. Expected something after the left token. Expected register or number after opening bracket. That should be good enough. Okay. Processing error. Okay. And then we return. Otherwise, we did something right, and we're going to want to check for the offset. And if we see a plus token, then we're going to process that, skip it, and we're going to check for a number token, and then we'll want to read in yet another one. And if we don't find it, if we don't find a closing bracket, we're going to do the same thing. Expected closing bracket after offset. Okay. Oops. Okay. I need to stop doing that and start doing this instead. Then we do. Okay. We can actually take this whole thing, copy it. So we either read in the plus symbol, need to validate this. We read in the plus symbol. The next token is a plus symbol. It needs to be one of these, or else we get an error. Expected number after plus. Yeah. For addressing operand. That's good enough. And then after this is just to check if the next token is a plus. Otherwise, it's a closing bracket. And then we'll do next token plus plus. Or else it's another error that we need to handle. Because that means there's no error, closing bracket. We could probably do this a lot better. I can't think of any ways to. So we'll just make it sloppy for now and we can refine it later. Expected closing bracket after addressed, register, or immediate. How about that? Okay. So this will fill out the entire operator. We'll have op offset, or it'll be 0. And then we'll fill in the integer right there. That's a lot of code. Oh well. Let's see if this works. Determine operand. Op1. We'll need to do, we should first check that it isn't, every time we do this, we'll check if tokens at I.type is less than token mov. If it's greater than or equal to, then it means that we're at another instruction. Else continue to the next loop. And we can do this for potentially every operator after this, up to 3. Depending on what the original operator is, and we can have a loop that determines that. So we can like do if top.type and that like equals token mov, then expect handle no more than like 3 operators. Like right now mov only handles 2, and so we can just set up a loop, like a for loop, and depending on the operator token we can set how many times we loop it to read in a certain number of operators. But we're not going to worry about that right now. We're just going to assume that we're going to be reading in 3 operators at a time. So we can do operand 1, op1, set it, 2, and 3. And we're going to hope that these advance the token to the next one. And then we can probably start disregarding all of these. And we'll need to move these outside of the loop. Okay. How about that? Again, really sloppy. And then we'll need to have a behavior tree here where we determine what the different operand types are. And we can do that with if op1 dot type equals operand register. And yeah, we can just do stuff like this. We're just going to handle 3 is going to be none for right now. If they're both registers, operand 1 and 2 are registers, and there's no type 3. We're going to do operator move register. We'll need the top type equals top move and all that. Then we'll set it to a move reg, else if, a bunch of stuff like this. Otherwise, it'll be move reg immediate. It'll be this. Kind of shrinks the code a little bit. Else if it's going to be an add register to register. Add. Just showing you a bunch of different ways you can handle this. Doesn't need to be one of those. You could use like the last brute force method. You could use this current method. We're going to keep refining this as we move forward. Add register, add immediate to a register. Okay, I think that should be everything. And then depending on what it is, I'm going to do op1 dot im or reg or im. I think that's it. Yeah, okay. Or it could also be, yeah, so then we'll need some stuff in here to handle. Well, this will always either be the register or immediate. And then the second value could be like if op1.type is greater than or equal to operand address register. That means that it could be like either a register or an immediate value. And then in 2, we'll need to put in the offset, like that, if it's addressed. Otherwise, something else to do. I'm being kind of robust right here. You don't need to do this. I think this is also wrong. Yeah, okay, so this is what I was talking about earlier. We can, we'll redo all this actually. Yeah. Okay, so we're getting there. Bear with me, just a few more steps and we should have refined our operand generation just enough. Little cleanup stream. Okay, otherwise it was a register. Immediate value. So that means a VM.bytecode. Oh man, I guess we could do an offset. Yeah, we could do a int bytecode offset. Yeah, why not? BCO. Why not? We'll just call that bytecode offset. Okay. It's gonna be BCO plus plus. This is horrible, dude. BCO plus plus. BCO plus plus. So it can be 0 here, 1 here, 2 here. And I think, well, yeah, that doesn't help. Because we'll still need some branching logic. Sorry. Just trying to get fancy with it. Otherwise, it'll be op2, reg, or immediate. Yeah. And then we'll do vm.bytecode 2. Is this not going to work? What the hell is the problem here, people? Start bytecode. Oh, oops. I fucked up and I deleted start bytecode earlier and I can't remember what it was. Oh. Okay, I remember what it was. Yeah, start bytecode. Is it not recognized? Start bytecode. It's valid. Start bytecode undeclared identifier in 2525. Equals like that. What the hell? What the hell is happening? Just get rid of this. Start bytecode. It's right here. Why do you have a problem with it? It's right here, bro. It's right here. Start import bytecode undeclared identifier. Oh, yeah. Man, I'm really tired. Okay, it's just a capitalization error. Okay. Yeah. Register immediate. And then we can do the same thing. If op 2, and then we'll do bytecode 3 is offset. And this will handle very basic instructions. We're not handling any operator 3s at this moment. And then, based on what that is, bytecode 2, 3. Register or immediate. Type, it could be a register or an immediate. Okay, so just so we can handle something like this, we could do if op2.type equals operand immediate, else if op2.type equals operand register. We'll just do this. Otherwise, we'll try and fit that into bytes 2 and 3. Because what if it's 16-bit? Again, this is kind of stupid. Else, it's going to, else if it's going to have a value greater than that. Did I lose connection? No. I see. Okay. Or else it's going to have the register or the immediate value plus the offset. Okay. And again, all of those numbers will be determined by the operator that it is up here. And again, we're only handling registers or immediates, and then we're going to add addressing once we know that everything that we got yesterday still works. This is just to add more flexibility for memory addressing. So we're going to store it as little endian. So this is the register or immediate. We can AND this with OXFF, and then we can shift this one up, or shift this part down and store it in the next byte as a little endian. I guess that's obvious. Little endian storage. Okay, and then let's just see what happens. Okay, we're still getting an error. That's fine. Okay, so we're doing something silly. Let's figure out where the problem starts exactly. We go into token count. We haven't read the top one yet. Top is going to be, remember, the operating token. It's going to be mauve. So next token I.type will be, let's see what it is. It's going to be a register token. So we're going to put a value of 0 in there, read the next token. Okay, that's fair. Yeah, okay, so it's a register token. Let's go to the next one. We will read in a register, an immediate token of 1. Okay, cool. Continue. We're going to, okay, op1 type is a register. What's the op2 type? Op2 type is an immediate. Okay, mauve registered to an immediate. We're going to store the values. It's going to be 0. It's an immediate value. We're going to store in bytecode. It's going to be 1. And then we're going to shift it up 8. Oh, okay. This is wrong, and I was thinking about this wrong. I we're shifting the value down by 8. Yeah, so won't that just store 0 there? Yeah, 2010. Yeah, okay. Oh, I think I'm just pulling it out of the registers wrong then when we go to evaluate it. Yeah, okay, so it's an immediate. And then in that case, in 2, I will have just 0. And then the third one, I'm going to want to shift it up 8. God, oh God, please. Okay. Yeah. We don't even need to do that. Okay, now let's see what happens. Okay, cool. So it runs. It runs fine. We don't crash anymore. We are doing all those operations fine, assumedly. So now I guess we could just start adding a bunch of tests in. And in that case, I'm going to want to reset the VM every time, like reset the registers, reset the memory, reset where the stack and the frame pointers are. So we can do something called, where do we define our VM? Yeah, okay. So right above it, why don't we just do this? Void reset VM. And we'll just have the global VM, and we're going to memset, we're just going to memset the entire thing. Why don't we? VM 0 size of VM. I think we need to make it a pointer. So we'll do VM undeclared identifier. That's because we don't declare it yet. Let's pass in a pointer to the VM. Yeah. Okay. And so that will clear everything. And then we should set the frame pointer. The frame pointer is going to equal, it'll point to max VM mem. We should like give it a little offset, just so that like if we put something to it immediately, we don't immediately address outside of memory. And we'll do the same for, sorry, that's a stack pointer. The frame pointer is going to be the same value, or start exactly where the stack pointer is. The bytecode will get cleared, the bytecode count will get cleared, the IP will get cleared, the registers will get cleared. The frame pointer and stack pointer will be reset. The memory will be cleared. Do 8 mem used, just to keep track of where we are in the memory. It'll be like an arena. It's the VM's arena. And then register, floating point registers, we're not using those yet. Okay, I think this should be fine. And now we can start making functions to test it. And so we can do, like we were doing in the other VM, we can do void test VM test mob add. I don't do that. And then we'll make it simple and stupid. And we'll have tests like this. Make sure this can run. You will reset VM and we'll send in a pointer to the global VM. Okay. And we'll just run this instead of having that all duplicated. Okay. See if it gets called, and then did the assertion still trigger? Cool. Okay. In the registers, yes. Okay, so that's as expected. We just made a little testing function. So now we can keep this function and just run it, continuously add on more functions as we add more functionality to this VM. And if we break something, then any one of these functions will also break, and so we can debug it from there. So just as a static battery of tests that we accumulate as we add more functionality, this will be like our testing infrastructure. And the more things we add, the more things we can test. So, what do we do now? We should probably also reset, like every time we test, we should reset. Well, we do reset the lines here. Let's reset. And I wish I could go to where those things are declared. We need to keep track of the parser state so we can reset that. This is everything that we're going to need to reset every single test. Vague idea of it. So we can just, the VM input, that won't change. The tokens, VM token count equals 0. Temp line equals 0. We have that. Parser line is going to be 0. I mean 1. Storage offset will be 0. All of these are indexed by all the numbers. So VM tokens is fine. VM bar storage is fine. Lines, tokens, VM line. Yeah. Okay, so we just want to reset those at the same time. Yeah. Not pretty. Maybe we could do void reset global state. Reset global VM state. Why not? We'll call it on here. We'll just call this function. Just to make it a bit cleaner. Then we could do VM tokens. Yeah, why don't we? Void run, I don't know, VM. What do we call this? Where we parse, get the tokens, emit the bytecode, and then run. That's like the entire stack. Parse, emit, run. Yeah, fuck it. Parse, emit, run. And then we'll send it the input string. So all we gotta do is just remember to wrap whatever text we define in these two functions, assert something at the end, and then we should be good. We can count, yeah. See if it still runs. The assertions are good, okay. Just to clean up the testing function so we don't need to constantly duplicate that stuff. Then all we care about right here is this stuff in the center, where we actually define the assembly code. So we could add, let's add push and pop tokens now. Let's add to the bottom, token push, token pop for the stack. Let's go to where, can we like go to all the instances of this? Set at the bottom right here. Percent 3D backslash n. Okay. We'll need to add it to this tree where we want to have push and pop with P's. P, else if, pop, which is 2, and push, which is 3. Go to pop, go to push, placeholders. problem. 1967. Okay. Keep forgetting something critical here. Oh yeah. Okay. Okay. So we added push and pop. What should we test next? I guess we can, yeah, I'll try and do addressing next. So, this will be really simple. Yeah. Let's do addressing. Move addressing. I'm gonna duplicate this. And so we're going to move a value of 1 into RO. And then we're going to address that and set 2 there. And then we're going to move into R1 and address the address of RO. And so that should be the same as moving 2 into R1. This is just basic addressing. And then we're going to test if the value of 2 is the value of register 1. Okay. We're going to set a breakpoint here. Print the tokens. So we found MOV, register, octothorpe. We're moving a value of 1 into register 0. We're moving into left bracket, register 0, right bracket, a value of 2. And then we're moving, yeah, L bracket, right bracket. Oh. Okay, yeah. Move register 1, yeah, the left and right brackets. Okay, just confused myself for a second. So we're setting 5 into register 1. What the hell? Am I not clearing the VM when we get here? It's in the VM. Bytecode count 12, frame pointer. Registers are 3 and 5. Huh. That's interesting. But he's not getting cleared. We're resetting the VM, and then in the VM, registers 3 and 5. Why is that happening? We're not mem setting correctly. Mem set VM. Okay, so right now, it makes sense that registers. Okay, after this happens, 3 and 5 will be in the registers, yeah. And then we mem set size of VM. VM still has 3 and 5 in those registers. Oh god. Size of VM. Am I not doing something right? How about now? Pretty please? Okay. I guess you don't want to put in the underscore global VM. You want to put in the size. Okay. Okay, now it's fine. Just a little typo. Gonna run it. Gonna see what happens. 1 should be in register 0. Okay, you see that. That's good. And then, oh, oopsie, I don't have, we need to add a check. It's not caught. We need to do printf unhandled instruction. And then we can do print line, print VM line. Unhandled instruction. We can just do a little printout of the operand type. please. You do op string. Yeah. We can do vm.ip. Yeah. Okay. And then we'll go to operand types or op types. Yeah. Well, let's add a few more. Now we'll have op mov. We'll need to have different types for if it's removing an immediate into an address or an immediate into a register. So this will be address, immediate, reg, address. You can't move an immediate, you can't move, this for example, that won't work. But I think every other case could. So this is a register, we'll do address register, address immediate, address register, register address. And then in those cases, we'll need to have like address register if it's like a register there or an immediate value. Yeah. Add reg, a dredg, immediate. Addim, immediate. Reg. Reg. Yeah. Kind of sloppy. You have this combinatorial explosion when you're doing it this way, where you just want to simplify every single possible operation into a tiny amount. Of course, we could add another type inside of this op type, like we could make a structure, and then inside of it we could add subtypes of like if it's a register or an immediate value, or you might even be able to collapse these, and we'll figure it out later. Just copy this over. Address register, yeah. Just to put an example next to it, to make it easier for us to understand what the hell exactly is happening. Immediate. These will both be registers. Yeah. And then the only other case would be register. Oh no, a register and a dred. Yeah. Wow. There's 6 total cases. Wowie zowie. I think there's only 6 total cases. Could be different. Does that make sense? I think that makes sense. And then inside all of these, we'll just assume that they have an offset of 0. Otherwise, we would need to add even more instructions. So we'll just assume that inside they have some kind of offset. Okay. And now we need to push all of these into that little op string function. Run VM, let's do const char op string. Just do int op. Switch op. Return null. Please. Default. I need to add the break, but I just do it out of habit. Remove all these comments, not like that. Okay. Case. Break. return that. I think this should work. Okay. Okay, so let's just assert unhandled chart. No, that's not it. Let's go to run VM, and right here we'll just assert 0. Fail immediately as soon as we hit something that we don't recognize. Okay, good. Op add register immediate. Okay. Op add register immediate. Let's add a little printf. Let's just print out the operation that we're running right now. Edit here. Let's do that at the top. Current instruction. And then we do like unhandled instruction. Okay. We can also like wrap it in that bold red reset stuff. Red. Reset. Okay. Cool. Current instruction none. That is not good. How is none handled? Current instruction none. I don't like that. Yeah, there's going to be a combinatorial explosion here. Because, like, what if we want to do, we'll want to have, like, these are 6 per any possible instructions. We'll have mov 32, mov, well, like, mov and mov 32 will default to the same thing. There will be mov 16, mov 8. If we want to handle different, moving different bytes around that are different sizes, we'll have add, sub, mul, div. For pop and jump, those will be individuals. We don't need to worry about that. Push. We're going to want to figure out how to compress this down later. But we'll get there when we get there. That'll be like a big hurdle that we're going to need to jump over. I keep getting distracted. What is current? Why is current instruction operated on? How could that be happening? It's the same thing. That didn't help. Just trying to cast it. Oh dear, I never made a day 7. I can fix that later. Current instruction off none. Mov add. None. Because the instruction pointer is 0. Okay. That's my bad. That's my bad. We got to do this instead. Okay. Okay. There we go. Okay. Because we set an immediate value in the register, but then when we start emitting, when we go to emitting them, we're never handling that case. Oh my god, determine operand. This is a, like, I look away for 5 minutes, and this is just a complete disaster. This is almost 100 lines, but I think that should handle most addressing cases. We'll just hope that that stays relatively stable, and then we'll need to add more cases right here. Yeah, this is still not good. I need to figure out a better way later. But it's mauve, and then we're going to have into register 1, we're going to move some 3 more of these. Yeah. We need to handle these. Operator mauve, address register, immediate. Op1 type is address reg. Operand type 2 is immediate. Okay. It's address immediate. Oh god. These are both immediates. Address immediate and operand immediate. Reg. Please. Reg. Immediate reg. There has to be a better way to do this. I keep saying that, whatever. Just commit to it, retard. Reg, address, reg. Oh, god. Mauve, reg, immediate. Okay. Wow. Let's see what happens now. Hey, okay. So we're still hitting an unhandled instruction where we have mauve, reg, immediate. Let's print out the current line too. Why don't we? We can do print VM line, and then we can have the line number, which would be VM IP divided by 4. So we can see exactly which line the error is happening on. Okay, VM line 1, when we move, VM instruction pointer is 4. Okay, yeah, we're going to want to add 1 to it because the line starts on +1. Okay. Okay, right here at line 2, we're moving an immediate value into an address register. Okay. Let's add a case for that. I just did something that I don't like. This will be mauve, address reg, immediate. Let's do a debug breakpoint here. Of course. Somehow delete that 1. Isn't that amazing? Okay. Okay, and then we also need to handle, well, let's just do it for all of them. code for all of these. Case break. Oh god. Okay. So for this case, in the vm.mem, you want to access register. So we're going to have a register, u8 reg1 equals vm bytecode vm.ip plus 1. We're also going to need to store the offset there, because they could contain offsets. No, I think I'm just confusing myself. We're all over the place. So if operand 1 is addressing via a register, then we're also going to want to store an offset there. Just in case, yes. Yes, okay. So we only add the offset if we're addressing, if it's an immediate, okay. So we're already accounting for that, okay. So we're going to want to, if the first one is an address, then we're also going to read out the offset. And then we're going to have the immediate, which will be at 3. Okay. And then what this is going to do, this is moving the immediate value into the memory that we're accessing. So we'll do vm.registers. We'll do address. I don't know what we should make it. We'll do registers, reg1 plus offset. And then that'll be the address. And that we're going to set to the immediate value. Like that. We're going to see if this holds for every other case. Of course. We paste it here, 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 here. Wow. Gets verbose fast. So we're going to move this case. We're reading an immediate with an offset, immediate 1, immediate 2. Okay. This will be immediate 1, immediate 2. Register. This will be reg 2. This will be an immediate offset with a register. Immediate reg. This will be an immediate set to the reg. Register, register. Reg 2. Reg 2. Okay. Okay, this is where it starts to change. These are all where the address comes first in the operand, and then this is where the address is second. So into register 1, we're going to set the value from memory. Equals vmmem at address. In register 2, yes. Well, no. Got it backwards. We read out the register first. This is something like mov register, then the brackets. Plus offset. So this will be register 1. This will be register 2 plus the offset. So we need to reorganize these. Offset. Address is register 2 plus the offset. Okay. I think that should work. If not, we'll debug it later. Same thing for here. Into register 1, we're moving an immediate. let's just see what happens. And of course, got an error. Yippee. Okay, let's see what the problem is. I'm gonna step in here. We parse everything. And start running it. The current instruction. I wish I could, yeah, why don't I just print out all of the instructions again? I don't know. Whatever. We'll see them as we advance through it. Let me also print out the line. Print the M line. Yeah. Do this one after another. Okay. So line, move that immediate value into register 1. This will set register 0 to 1. Good. And then the next one, we're going to move an immediate value into the address referenced at register 1. And so register 1 will be 0. The offset will be 0. The immediate value will be... Why isn't it 2? Okay, so we're not storing it correctly when we originally set up the operands. Let's figure out what we set this. Set a breakpoint here, and we will... Oh my god, what did I do? Okay. So we hit the end of file, move address register immediate. The op type, register or immediate. Let's also print out the line here. What's stopping us? We can just say parsing line. Yeah, whatever. Printf parsing line. And then we'll do that. Bytecode count. Parsing line 1, parsing line 2. Okay. So as we're parsing line 2, we see that it's moving an immediate into an addressed register. And so we're going to check that register or immediate is, yeah, that's register 0. Operand 1 is an address register. It's going to have an offset of 0. And then, okay, well, we didn't add the second one. Okay. Otherwise it was register or immediate. And we're going to need some more if statements here. Wow. Okay. That's fine. Just keep slapping it on until op2.type equals operand immediate. That's if op2.type equals operand register. Okay. And then we'll just be dealing with the third instruction. To reg or im. Same thing here. Well, I guess we don't even need something like that because, yeah. Yeah. Can we just boost this up later? Okay, hey, look at that. Okay, so now it's working. I don't even know if this is really a better case. Like, this is just a huge if else, if else, if else, if else. We'll need to... I don't think this is any better. I mean, it just, we made it a little bit more flexible so we can handle addressing. We'll need to try some kind of different implementation next time we stream, because this is a lot to keep track of, but we'll figure it out. Let's just step through that new test that we made. Let's do VM test, move address. Okay. Step into it. Yeah. Yeah. Come on. Please. Run VM. Current instruction. Into register 0, removing an immediate of 1. Come on, show me registers. Please show me registers. Dear God, show me registers. VM.registers. Okay. You see 1. Let's go to the next instruction. Moving an immediate into the memory referenced by register 1. So in memory address 1, we're going to move a value of 2. And in this case, we're going to need to, later when we want to handle like actually expanding it to 4 bytes, do we need to do that now? We should probably do that now. Well, later once we want to handle immediates to do expand to setting 4 bytes at a time for standard mod. Default. We don't need to worry about it now. Of course, it's going to offset all the instructions. Let's go back here, step into it, run VM, do that current instruction. You see 1 in there. Next instruction. You see 2 in the memory address of 1, and the final instruction from an offset of, an address of 1, because remember, register 2, register 0, the address of register 0 is 1, which means that the address 1, the memory reference there, we're going to be setting into register 1. And so then you see that register 1 is set to 2, and then we fire the assertion where that memory is in 2. So we can handle very basic, brittle memory addressing in the virtual machine now. So we can work with memory and our fixed array. Of course, we need to check if it's outside of range, because like what if I do something like -2, for example. Can we handle negative? I don't think we can handle negative numbers, actually. That'll be something that we need to do. Yeah. Well, no, do we even want negative numbers? I'm not sure. We should be able to work with them. Yeah, we should have the ability to handle negative numbers. That's tricky. I never thought of that. We could add like a negation step where we negate whatever value it is. That'll need to be an instruction. So that's something we'll need to think about. But at the moment, for unsigned integers, we can now address memory. So I think I can end it there. That's good enough for today. We added some more slop. Again, this is all experimental. I'm not sure what method we'll use eventually, but we got a little bit more functionality today. So there's a lot to think about. But I think that's good enough for now. And if you want to work on this yourself, I have the repo linked in the description. You can download it, run it, as long as you're on Windows. Like I think the defines I made up here, they're brittle, and I think they would default like long. I think defaults to 64 on Linux, so you'll need to adjust that if you go to Linux. Defines might be U64. So, just a little warning. There's a lot of stuff you'll need to keep in mind, but feel free to experiment with this. You have the link to the GitHub. I'll be back eventually. Can't say when, and we'll try to work on this more and figure out if we have the right architecture or if we need to fix it. But until then, catch you later. Thanks for watching. See you later, guys. Bye-bye.